We're now going to learn about relational algebra, the theoretical foundation of relational databases. Relational algebra has its roots in set theory, and it provides us with an abstract mathematical model to reason about data. We're going to represent data as a collection of relations, each of which is a set of tuples modeled by a number of different named attributes. Now, this mathematical perspective will give us a concise and consistent way to describe and manipulate our data regardless of its scale and complexity. The central concept here is that of a relation. In the context of relational algebra, a relation is a set of tuples, and each tuple contains a fixed number of attributes. Sort of as an intuitive example, consider a spreadsheet table. Each row corresponds to a tuple, giving a value for each of a set of attributes. Each column represents one of those attributes. The relation as a whole is a set of such tuples constituting an entire set of data. The idea is each tuple represents data about one particular thing, and each attribute represents one type of information that we're storing about these things. Each relation has a characteristic set of such attributes, altogether called its schema. Relational algebra defines a set of basic operations that transform relations into other relations, giving a rigorous mathematical model for updating and querying the data. Having such a model enables us to reason formally about the properties of our database systems. We can then prove correctness, optimize performance, and even devise new operations to suit our evolving needs. Indeed, the basic operations of relational algebra, which we'll learn about, select, project, union, intersection, set difference, Cartesian product, and rename, these are the atomic building blocks of relational algebra. All of the complex operations that we want on our data can be constructed just out of this small set. Consider an intricate query we might want that could involve a combination of extracting specific records, combining different relations, or filtering data based on multiple and complicated conditions. Regardless how complicated we get, we can always construct it by piecing together these basic operations of relational algebra. It thus gives us a rigorous mathematical foundation for our database systems. Each basic operation has a precisely defined behavior and provable properties. Since complex operations are always built out of these simple operations, we can then mathematically verify that any such operation will produce its intended results, that it won't violate the integrity of our data, and that it will behave consistently across different database systems, as long as these basic operations are correctly implemented. So with this mathematical model as our foundation, we'll be able to approach the design and implementation of relational databases with confidence and precision. Now, let's dive in.